Hello, everyone. This is part 2 of my interview with Dominic Chang, a Jamaican born and raised theoretical physicist at Harvard. So this is a very special episode with one of, my own coming from Jamaica. So please continue to watch this part of the episode. I hope you like and subscribe, and please check the description box below to see Dominic's responses to specific questions in part 2 of this episode. I hope you enjoy. So now I want to pivot into the research aspect of this interview. So this is what I think is really cool because I think theoretical physics is just so far beyond me. I'm an experimentalist. I do wet lab research. Ask me how to synthesize something or extract something out of extract some compound out of some matrix. I can do it, but I don't know. Theoretical physics is just like way beyond.
No, it's like any other thing.
I'm going to dive in and hopefully you can help me understand what you actually study. So now when we spoke previously, you told me that you were at the Brookhaven National Labs and are now working with the Event Horizon Telescope, which is a team of people who recently discovered the image of an actual black hole, the one that's in your background picture, I'm assuming.
Yep.
Which became viral. I remember hearing it on the BBC. I actually remember listening to this on the BBC while I was in the gym one morning. Global News podcast. So speaking with a scientist working with this group and actually knowing them from high school on the island of Jamaica is just very, very, very coincidental. It's so coincidental that I met you from high school, but you're working with this lab. I don't know. Explain to us how your research pushes the envelope of our understanding of the universe. Why is this important for us as a humanity to know, like, the physics behind black holes and,
So I actually spent a lot of time thinking about this question. I think so. When it comes to there's a very much bigger, deeper philosophical question here. It's like when it comes to physics, a lot of the things that we research, it doesn't seem like it has any obvious application to real life, but it usually and inevitably does end up having some sort of application. It's just not obvious in immediately when you're doing the research. The thing that's cool about the black hole that we looked at is that it's a test of strong field general relativity. Like, this is the only experiment that's testing general relativity in the region of
extremes.
Yeah, in this extreme. And the thing is that, as I mentioned before, you can come up with a theory. It doesn't mean it's always correct. It's usually correct within some regime. Like, Newtonian physics is correct within the classical regime at relatively at okay energies, and as long as you don't do too much.
Okay.
But general relativity is it's still a classical theory, but it deals with these massive, high concentration of energy and mass in space, and it allows us to understanding that would allow us to understand our universe better, and understanding our universe better is good for a lot of things. I mean, developing technologies, entertaining people if you like it, I guess, and it does have immediate applications. I mean, one of the most immediate uses of general relativity that I can think of is with GPSs. It's known that there's a time delay because of Earth's gravitational field and the motion of satellites in space. between someone on Earth and the GPS goes going around.
Oh wow! I never knew
so
about
you actually
that.
have to do relativistic calculations in order to compensate for the time delay.
Oh wow, that's
and
cool.
yeah, and the thing is that if you don't know the theory before, you won't be able to do those calculations.
And you'll be wondering why it's wrong all the time, or if there's some
much.
error.
Yeah. I mean, there are other. It's hard for me to tell you exactly how this research would fit into technology now, but I definitely strongly believe it will. I mean, there's some machine learning and statistics is involved in just like generating this image, and just those techniques could probably have industry applications, like immediate industry applications.
I mean, to be honest, I think it's an important science to pursue now. I always think of physics as something of the science that scientists that study physics now are actually pushing the boundaries that we will have to face like 100 years from now.
Yeah, I guess like if I were to give good examples of where physics research has led to new technologies, I mean the World Wide Web pretty much exists because of. So I was working with the Atlas collaboration. I was at Brookhaven National Lab. The Atlas collaboration is an experiment at the Large Hadron Collider in CERN. So I've actually been to Geneva and seen the experiment.
I've been to CERN too, but not because I actually knew what they were doing, just to see it.
Oh, I see. It's a very beautiful place.
It is.
I think I'd go there even if I was working there. It's very pretty. But the thing that came out of CERN actually is the World Wide Web. Like they had this issue where they had an experiment, and the experiment collects a lot of data, and before what they used to do is that they used to print it all on sheets of paper, put it on a bicycle, and it would be someone's job to ride the bicycle back and forth. And of course, this had issues. So they had to come up with some sort of method to get the information from one place without physically transporting it. And one of the solutions they came up with is the World Wide Web.
Yeah.
Or like not the World Wide Web, but some predecessor to it.
Yeah.
In fact, I think. Oh, I should look these up again to make sure I'm not giving any false information. But I think also the first either web video or the first image was sent over machines over the network at CERN.
Okay. Let me.
Yeah. So.
Yeah. Continue.
In order to like try and solve these problems, sometimes you come up with interesting technologies. I mean, another thing that came out of physics, I think a Nobel Prize was awarded 3 years ago for the blue LED in physics, and there's a transistor. I think how the transistor came about is kind of interesting. So there's these vacuum tubes that existed that physicists used to kind of use to study electrons. So you just have a metal element, you heat it up, and you put a electric potential across it, and it gets so hot that the electrons kind of just get they just jump off of the heated filament because it's so hot. I think one day somebody realized that because you put the electric field across it, the electrons are negatively charged, it'll flow towards a positive terminal that you have, and they use that to create basically a one-way flowing circuit, because electrons will want to flow through positive, but if you run the current backwards, it won't flow all the way. And that was like the first transistor, and that was also born out of physics. And there are various other things. There's all the countless examples you can come up with, but of course, at the time that you're doing the research, you don't immediately know what the technological application is. Yeah.
I mean, it's the same thing, like as you said, Einstein's theory of relativity would have come out, you said 1915?
General relativity came out in 1950. It's kind of interesting because that in particular, like the question he was trying to solve was how does what is gravity is basically the question he was asking. And he was trying to see if he could come up with a good calculation that better approximates the perihelion shift in Mercury. I think back then, if you use Newtonian gravity to calculate Mercury's trajectory, you'd be slightly off, And people knew this for hundreds of years, and no one knew why. And Einstein was just trying to solve this question. He came up with the thing, and now it has a lot of application.
Exactly. So it's the same thing about why you're studying black holes now. The application isn't necessarily immediately understood, which that can also be argued. But in the maybe 100 years from now, because it would have been 2015, 2015 would have been 100 years since Einstein found this solution, I guess. Then maybe 100 years from now, we'll find out something else that we didn't realize. So
I guess you could even say there's application now, because if you watched Interstellar,
love that movie. That was one of my favorite. That's actually my favorite space movie. Period.
Yeah, the black hole that's generated there is, I mean, it's not a super accurate image of a black hole, but it is generated from those equations for general relativity.
Yeah, I heard about that. Yeah,
it's generated using only lensing effects, and that's those are calculations that we actually have to do at the EHT all the time when we're modeling black holes.
Awesome, that's cool. So I have one science question that I want you to answer. Can you tell us of the singularity that exists at the center of a black hole? What is it? What is the singularity?
Yeah. So, I've been trying to figure out how to answer this question. So the thing is that whenever you hear people talk about black holes, you hear them talk about the singularity all the time, right?
Yes.
There's a singularity at the center of a black hole. But the thing is that I think this is where a lot of physicists are using their language to lead people astray. I think people are thinking oh, there's this dot at the center of
That's what I'm thinking.
Yeah. There's a black hole and there's this dot at the center where all hell breaks loose. But that's not really what it is. When people talk about a singularity, it's really a singularity in the models, in the mathematical models we build. So as I mentioned before, the models we build are only applicable in some specific regimes, and we don't know everything about the universe. And one of the things we don't know about is what happens at the center of the black hole, and how that pops up in general relativity is that a lot of black hole solutions have a singularity, it just blows up. You get an infinity in the middle. So that's what they mean. That's what the singularity is.
Okay.
Yeah. So at the center of the black hole, the real answer is we have no idea what's there. We have no clue. There's some theories out there. There are black hole solutions you can write down that do not have singularities. There's some extensions to general relativity that come out of string theory that also don't have singularities. People don't like that there's singularities because it's just a sign that we can't predict things there. And but you could also look at it as it's a sign that there's new physics to be found.
Okay. So then, can I ask a question? If you using your imagination, what do you think would be at the center of, forget the physics, just tell me what
I guess so what's kind of appealing is some of these ideas of wormholes. So one of the ideas the black hole is kind of like an interstellar wormhole, and instead of a singularity, it's like a bridge to another universe.
Okay.
A universe that's separated from our universe, of course, but only linked by the black hole. So that's kind of a cool idea.
A cool idea. Okay.
Yeah.
I'll believe that until someone figures it out, I guess. I don't know. All right. Cool. So, lastly, Dominic, this is my favorite question. for all of my interviews. Can you tell us of a misconception of graduate school that you would like to dispel to the general public and viewers, particularly maybe viewers in Jamaica, that you'd like to speak to? Some misconception, so that maybe they'll be interested in coming to graduate school and studying physics like you.
So I think this question might depend a little bit on what you're doing, but for me, I remember when I was applying for graduate school, I imagined that I'd be working like 24/7, doing nothing but like doing research on the thing I'm doing, and I won't have any spare time or anything. And one, that's not true, and two, it's not good if that was true, because what I noticed is that like so you can sort of just create as much work for yourself as you want. So like even if you have spare time, you could just like easily just fill it up with work. But the problem with that is you become very inefficient. So it's actually not good to work all the time. Like you get stuck in a rut. Maybe you might be approaching a problem from the wrong way. And this is the thing about doing a PhD. A lot of the times you're attacking a problem, not a puzzle. A puzzle has a solution. A problem doesn't necessarily have a solution. Mm-hmm. And if you're doing the wrong thing to solve the problem and you get stuck on doing that, you won't solve it if there is a solution. So sometimes you kind of need to take a break, take a step back, look at the big picture, reevaluate things, and that will either help you figure out a new approach, or that may help you like reformulate the problem. Maybe the way how you originally stated the problem actually didn't have a solution, but you can change it in such a way, give a more specific statement of it so that it does have a solution. And then that way you'd actually be able to become more efficient. So the misconception I want to put out there is that you cannot, you should not, and you cannot be working all the time.
I like that. I would say my first couple years of my PhD, I thought that in order to be a good student, I had to be here all the time, in lab all the time, and that's definitely not true. So thank you for saying that. Okay, Dominic, this is the interview. So thank you for sparing time to be part of this science communication effort, and I hope you enjoyed it, and all the best.
All right, thanks. All right, I hope the viewers will get something good out of this.
Of course they will. This was great. Thank you, man. All right. See you.
Thank you for watching part 2 of my episode with Dominic Chang, and I hope you enjoyed. Please like and subscribe to my channel. It helps me so much to continue to do this work. So I hope to see you next week. On Friday is when I upload a video, and can't wait to see you next week.